Along comes a Danish astronomer named Tycho Brahe. And Tycho Brahe is in many ways credited as to being an extremely good observer of the cosmos. And so he made very accurate measurements and accurate charts of the positions of the planets and positions of the stars. In fact, one of the chief tools for measuring those things, called the sextant, he actually made considerable improvements on in order to improve its accuracy. We understand that Tycho Brahe's model view of the universe was still fairly geocentric, though he modified it slightly to Copernicus's view. But that's not a particular discussion point at the moment. But what's really important is that Tycho Brahe, he made some very precise measurements over many, many years of the various positions of the planets. He was very jealous of keeping those results, not wanting other astronomers to particularly use them. He later on employed Johannes Kepler, a well-known mathematician and astronomer, but Johannes Kepler wasn't privy to all the data that Tycho Brahe actually had taken. Upon Tycho Brahe's death, Johannes Kepler had full access to the data. And that's where we actually come into Kepler's planetary laws of motion. So Johannes Kepler used the data that Tycho Brahe had collated to look at the understanding of the motion of the planets. And by careful mathematical analysis of the data, he came to a really important conclusion. And that is that the planets aren't actually going around the sun in a perfect circle, but they're going around in an ellipse. And that is in fact the first law of planetary motion, that the planets that are revolving around the sun are revolving around in ellipses and not perfect circles. Now, I have exaggerated here what an ellipse is. In this case, you can consider an ellipse as really as a squashed down circle. Planetary number 3 actually looks at the relationship between various planets around the sun. And in fact, the planetary law of motion number 3 is basically true for any particular object revolving around a central body. So although we are here examining the case where we have various planets revolving around the sun, we can do the same concept of Kepler's third law in terms of, let's say, various satellites around the Earth. But what is Kepler's third law all about? Well, before we actually explain Kepler's third law, we need to basically understand that we have a number of measurements here. And if I were to work out this radius over here, the distance here is what we call r, but what we actually refer to is what we call the semi-major axis of its orbit. So what we say is, well, let's say we call this R1 over here, and then we have the next one over here where we have R2 over here. We have two radiuses. Now clearly this radius is smaller than this radius. Now the planet going around the sun will have a particular period, and that period we'll call T1. So in other words, that's simply the time it takes to go around one loop. For this planet, it is equal to T2, and clearly we understand that it's going to take longer for the understanding the fact that it has to travel a lot further. And so Kepler for many years played around with the numbers that he had available to him to work out, is there a relationship between these four variables? And eventually he did work out this. He basically said if you have the radius of the first one and you cube it, and you divided it by the period of the first one and square it, then that value is the same value if you did this for another particular planet or object or satellite in the orbit. So in other words, there is a constant relationship between the cube of the radius and the square of the orbit. In other words, this is constant. So in other words, if you work out any planet, in this particular case of the sun, work out its period, work out its radius, then the relationship between the two is r cubed over t squared is a constant value. It's the same for every particular planet revolving around a common body, which is the sun in this case. So clearly, if you increase the radius, the period also increases, but as you can see, it does not increase at the same factor. Have a look at this table over here. Here we've got the table of the average distances of various planets away from the sun and the time it takes for one complete revolution. So you can see the Earth here is 365.2 days. Now what would you get if you were to work out the r cubed over t squared? Well, Kepler and Newton would say that the values here are exactly the same. Take a moment to work out what that value is. Now if you did this case, and I'm going to do this case for Mercury, you would get 57.9 cubed over 88 squared, and you would get a value of about 25. Now remember, these are averages here, so if you then did that for any subsequent value, you should get roughly 25. Now I want to...
Όπως είδαμε στα προηγούμενα βίντεο, ο Τυχο Μπραχε κατέγραψε με μεγάλη ακρίβεια κινήσεις πλανητών. Μετά ήρθε η σειρά του Κέπλερ να μελετήσει προσεκτικά όλες αυτές τις καταγραφές, ο οποίος κατέληξε στους νόμους που περιγράφτηκαν προηγουμένως, και ήρθε η σειρά του Νιούτον, του Νεύτωνα, να αποδείξει και με βάση τους νόμους της βαρύτητας ότι αυτό πράγματι ισχύει. Αυτό που ζητάμε από εσάς είναι να παρατηρήσετε προσεκτικά αυτό το πίνακα και να προσπαθήσετε να δικαιολογήσετε αυτό που ο Κέπλερ περιέγραψε ως τρίτο νόμο. Δηλαδή να κάνετε τον υπολογισμό που φαίνεται εδώ, δηλαδή να υπολογίσετε το λόγο του R3 της απόστασης, δηλαδή της μέσης απόστασης του πλανήτη στην τρίτη προς το τετράγωνο, δηλαδή προς την περίοδο του πλανήτη στο τετράγωνο. Καλή δουλειά!